I'm Duncan Foley, and this is the new school for social research in the spring of 2016. This is a course, Advanced Microeconomics 2, GECO, which is the designator for PhD courses 6219. As an experiment, and with the help of the Institute for New Economic Thinking, we are going to video this course, and that will include both my talking and also what I find is one of the most interesting things about New School courses is questions and colloquies with the students who are sitting in. And so I don't want to put anybody on the spot, but I would particularly encourage you to ask questions and colloquies. I sometimes say that people are reluctant to ask questions, but they should do it as a kind of public good, because whatever question is on your mind is probably on another student's mind. So you should feel free to ask a question, and that helps everybody understand more. In this case, you can imagine yourself asking questions for whoever might be looking at this video, which might be anybody. So anything that occurs to you that's not clear, you can represent as much of humanity as you think might ever look at this video in that way.
Hi, I'm Jiang Wei, and I'm a PhD student at the New School of Social Research, and I'm from South Korea. Thank you.
Hi, I'm Richard. I'm from Greece, and I'm doing my master's here.
My name is Marjan. I'm from Iran, and I'm a PhD student.
My name is Jose. I am from Colombia, and I am a PhD student.
Hi, I am İlker Aslantepe. I am a PhD student in economics. I am from Turkey.
My name is Kyle Moore. I'm a PhD student. I'm from South Carolina.
My name is Keith Blackwell. I'm a PhD student as well, and I'm from North Carolina.
Hi. My name is Sozam.
Diversity cheer here.
My name is Sozam Ömer, third year PhD student at the New School and from Turkey.
I'm Matthew. I'm a PhD student from Texas, although I did also grow up partly in North Carolina. That's to continue.
My name is Daniel. I'm a PhD student at the New School, and I'm from Queens.
My name is Hale. I'm a visiting scholar here. I'm from Turkey.
I am Daniel Torres. I'm a PhD student as well, and I'm from Mexico.
Hi, my name is Francisco Aldape. I'm a PhD student, and I'm also from Mexico.
Hi, my name is Oriol. I'm a second year PhD student in the New School and from Spain.
One second. I'm Williams, a PhD student, born in London and grew up in the Bronx.
Let me tell you a little bit about my goals with this course. I found myself, especially over the last couple of years, as the result of doing some work with Sam Bowles and co-author Simon Halliday on Bowles's book Microeconomics, which I've been working some on rewriting into an undergraduate textbook. I suddenly had a kind of an epiphany way into this process, but a couple of years ago, which helped me organize a good deal of my thinking about some fundamental issues in classical and Keynesian economics, and around some of the themes of the theoretical themes of this of Bowles's microeconomics, which are actually themes that appear elsewhere in the literature, and I'll try to tell you. But mostly the issues have to do with information theory and the introduction of information theory in a systematic way into economics, and what's called social interaction or social coordination models, which are also are certainly well known in the field, but I have started to put them together in a way that I think is fairly distinctive and, as I say, helpful in understanding, synthesizing to a certain degree, some major themes in heterodox economics. So I thought that I would try to put this together in the form of this course. I've discovered in the past in teaching this material that I tend to go too fast, and I tend to assume that people who are listening to me or reading what I've written know more than they probably actually do about some of the topics that I bring up. So in this course, I'm going to be at something of pains to be sure that I go over the fundamentals before I do applications and try to do everything in order so that the ideas are really available. And because these ideas, although they're not, as I say, not novel or new, they're in the literature, they are not part of the standard economics curriculum at this time. I think it's important for me to go over them carefully and in order. So I'm going to start this course with a review or overview of some of the preliminary technical topics that are fundamental to the rest of the course, including a little bit about philosophy of science and social science, a little bit of review of Bayesian probability, just to make sure that we are using the same terminology clearly about probability theory, and also elementary information theory, including the basic idea of Shannon entropy and its definition. So that's what's called Lecture 1. I might even finish Lecture 1 before the end of this class, in which case I'll just go right ahead to Lecture 2. The theme of the course is the theoretical and empirical explanation of the relation of aggregate and individual behavior in social situations. So in a way, what this approach is an alternative to general equilibrium theory. It's another way of organizing rigorously and systematically the question of the theoretical relationship between individual behavior and social outcomes. And I'll try to both give you the building blocks of that and then do enough applications of it so that you can see how it works. But really, the payoff for me is only going to be if people pick this up themselves and start to use it in their own thinking and in their own research. The big building blocks are the next topics of the course, the first two topics that we'll do systematically. One is called entropy, I call it the entropy constrained behavior model. In the economics literature, it sometimes is called rational inattention. Christopher Sims has written a number of, and his associates have written a number of papers under that. And what the entropy constrained behavior model does is it applies information theory to individual behavior, and therefore gives us a way of thinking about individual behavior which is a little different from the usual decision theory. In fact, it's quite different, although it bears some close relation to ordinary decision theory. The second one is the social interaction model. And this is a way of representing the situation of a typical individual in a social context. And it turns out, although it's something of a gadget, that is, it's a simple little way of putting this together, it turns out to be remarkably powerful in answering a lot of questions that come up in classical and Keynesian economics, heterodox post-Keynesian economics. So after we go over these basic building blocks carefully, we'll turn to applying these ideas to fundamental problems in political economy. The first problem is the theory of decentralized, spontaneous, organization of an economy in which production is specialized through a division of labor. So we're returning basically here to Adam Smith and the developments of Smith's ideas, especially in Marx, in Karl Marx, which I think are very closely connected, and I'll try to explain why this way of looking at it brings out those connections. We're going to use these basic tools, the entropy-constrained behavior and the social interaction model, particularly to examine the theory of money and the question of monetary neutrality at this very basic level of the Smithian economy. So that's one application. Then we're going to extend the analysis to look at capitalist economies. In capitalist economies, the typical producer gets divided up into a capitalist and wage laborers, which is a typical kind of bifurcation, as you'll see in this social interaction approach. And at that point, we can apply the social interaction model to the question of the typical capitalist firm among many capitalist firms, either the whole class of capitalist firms or a particular industry of capitalist firms, and we'll try to understand what the social interaction model has to say about that. I believe that that actually gives the key to one way of thinking about such topics as the Marx's discussion of the tendency of the rate of profit to fall, which has this strongly flavor of the social interaction model. Then I'll take up the study of advanced industrial capitalist economies along the lines of Keynes and Keynes's research associate Richard Kahn in the general theory, and we'll also talk about how that leads into the development of post-Keynesian economics and what you might call the micro-foundations, micro-foundations for post-Keynesian economics, in which the social coordination problem becomes a theory of aggregate demand fluctuations. Okay, and then we'll look, if we have time in the course, how long all this is going to take is a little uncertain to me, but we'll see how fast it goes, to looking at some revisions of marginalist economics and neoclassical economics, with particular focus on what information theory can tell us about distribution, especially distribution of income and wealth. And there are some very interesting applications along those lines. And if we have time, the last few lectures of the course, I will try to explain some more general principles of theory selection and theory construction that are closely related to this general set of ideas. So here's my trigger warning for the course. Learning the material in this course may change the way you understand political economy and the interpretation of economic data irreversibly, and make it impossible for you to maintain the views you now hold on those subjects. Learning can be a painful and stressful process that is traumatic to those who cling uncritically to received ideas. So you have been warned, and you've signed this release, but okay, so let's move on into the actual substance here of this lecture 1, which I call Preliminaries. And the first slide I'd like to talk about is a little bit about the philosophy of social science, just as a general background so that you know where I'm coming from in my thinking about this. I have the view that social sciences differ essentially from natural sciences. So that's not everybody believes that. Some people believe that the social sciences can be seamlessly integrated with natural science or be seen as a kind of an extension of natural science. But the reason that I think that is a sort of Hegelian reason, which is that the object of study, that is human society, includes the investigator. which in the broad abstract sense is the human mind. So social sciences have a self-referential character that's not present in the natural sciences. When Gauss or Newton study the orbit of the planets are not them, and there's a, it's a different situation than when we look at the way that our own societies work. One aspect of this self-referential character, which I discuss quite a bit in this book, Adam's Fallacy, if you're interested in looking further into that, is that social science has a kind of value-laden character which natural science can hope to avoid. It's very difficult to say this properly because it begins to sound as though you're saying that natural sciences don't have values. Natural sciences do have values because the natural sciences are social enterprises, and therefore the choice of topics, the way that natural scientists pose questions and so forth has a very strong input of values. But it doesn't necessarily have the self-referential character that is inescapable, in my view, in social science. But the bottom line here is that social sciences can incorporate important methods and ways of thinking from natural science, but have to transcend them in some way. And this is a sort of an apology for the fact that a lot of the material in the course comes from natural science ideas like information theory and other dynamical systems theory. But I want to emphasize that I view these things in a context where we're not trying to reduce social sciences and social interactions simply to those mechanical or mathematical aspects, but that it's in this broader context. Here's an example, because this is an example that we'll use quite a bit in the course, which is statistical physics. And one reason why the course has material in it that's more somewhat new and challenging is because the economics curriculum has incorporated a lot of methods of mathematical physics. For example, constrained optimization, which comes out of thermodynamics. But curiously enough, when people like Paul Samuelson imported these ideas from statistical physics, they did not import the idea of statistical fluctuations into economics. And in this respect, economics is a rather, if I wouldn't say backward, but it's a rather isolated intellectual enterprise because it has a different concept, for example, of equilibrium from most other sciences. Economics shares with physics the problem of studying aggregation. This example of thermodynamics, like, okay, what do you do about studying the physics of gas? Okay, so you have this gas that's confined, let's say, in some kind of a cylinder or something like that. And if you're an atomist, which actually at the time that statistical physics started, atoms and molecules were not totally well accepted as physical reality. It was only after the development of thermodynamics that really became a widespread point of view. But then if you believe that you're studying a whole big complex of molecules, interacting molecules, then statistical physics, statistical mechanics, or thermodynamics of gases is a problem of aggregation, very much like the problem of understanding the relation between individual firm and household behavior in economics and understanding macroeconomics. But the way that physicists do it is quite different from the way that general equilibrium theory does it. We'll talk in detail about how statistical physics approaches these kinds of problems and how similar kinds of ideas can be used. So statistical physics can illuminate problems of aggregation in social systems with many degrees of freedom. But what's the big significant difference? Molecules don't know where they're going. Molecules are not saving for retirement. They're not buying houses. They're not trying to get jobs or acquire skills in the labor market. Whereas human beings are. They're not passive physical particles that are simply trying to enact the Newtonian laws of motion. So it would be a reductive mistake to analyze social aggregation problems without taking into account purposefulness, intelligence, and planning on the part of the human agents whose behavior we're trying to aggregate. This social interaction model that we'll look at probably in 2 weeks in more detail is intended to pose this question very sharply and in a way that, but in a simple way where you can understand it. So what is my philosophy of science? I would also like to just say a couple of words about that, because that's controversial among social scientists and among economists. I tend to adopt the point of view of physicists on this, which is that the high road of science is the dialectical interplay between theory and observation or experimentation. And that you cannot do real science successfully unless you have the goal of explaining some specific data. So I tend to be a very data-oriented social scientist at a certain level, despite the fact that I mostly do theory, but that's where we are. So the basic paradigm here is this paradigm that science explains by organizing phenomenal observations and experience in terms of theories that have some explanatory power. And as we go into this more, I'll be much more specific about what type of explanatory power theories really have, especially these statistical theories. Basically, the explanatory theory of explanatory power of statistical theories lies in the concept of constraints. And I'll give you some examples of that in a moment, or a little bit down the road. But the notion is exactly that what we know about the world, what the causal elements in the world can be described in terms of constraints. In the context of social science, it turns out that maximizing behavior or purposeful behavior is actually a constraint. It has the same role as a constraint in statistical physics. So and this is, we'll talk about this some more when we get to the entropy constrained behavior model that I'm heading for. Another very important theme for me is parsimony. That is, that good theories are parsimonious. They avoid unnecessary complications. They respect Occam's razor. Occam said, don't multiply concepts unnecessarily. So this approach tries to strip things down as much as possible and to find the minimal theory that's required to explain any particular class of phenomena. When we look at Smithian specialization and the division of labor, for example, the question is, what's the simplest model in which you can understand the division of labor? Obviously, the division of labor has a huge amount of complications when we look at its concrete manifestation in the real world. But the idea is abstractly to boil it down to, as much as possible, the simplest elements in order to get theoretical insights. Okay, let me that's the end of the philosophy part. thank goodness. I imagine many people are thinking. But does anybody want to ask a question or pursue any of those ideas? Kyle.
What do you think about maximization as a valid behavioral rule in general?
Well, I think that it is almost indispensable, but as we'll see when we get to the entropy constrained part, the way that we do maximization is too narrow, is too narrow, and when you include realistic and very well attested behavioral regularities about entropy into it, then you start to get the kind of constraints that are very helpful. And I'll try to give you some examples of that. But it does not, and maximization of one type or another is very central to these theories. That's it for that? Okay. Well, then the next topic is probability. And the main point here is just to try to get terminology straight and have a kind of a playing field of a language that we can use in the course that won't be confusing and that won't be too confusing. But the idea of probability is inherently, as you know, probably very confusing. I'm going to use the term probability in the strict sense, and I'll try to be as consistent about this as I can, but I know I will make some slips. In the sense of degree of belief. So I'm going to use probability in the Bayesian, what's often called the Bayesian or Laplacian sense. That is, that it represents the degree of belief or the information state of a particular observer. It is not a characteristic of the external world. Okay, it's not something that's built into the external world. It's inherently a way of thinking about the relationship between an observer and the world. With this concept of probability, we can coherently refer to the probability of pretty much anything you can talk about. We can talk about the probability of single unrepeatable events. What's the probability that an asteroid is going to hit the Earth and destroy it in the next 10,000 years or whatever, something of that kind, which is not ever going to be repeated, because once the Earth gets destroyed by an asteroid, it's not going to be there to go through the experience again, right? So it's a single unrepeatable event. What's the probability that there's going to be a recession by the second or third quarter of 2016 in the US economy? Now that is a single unrepeatable event, because we're not going to come back to 2016 again. We're only going to go through 2016 once, but I believe that it's possible to talk sensibly about the probability. I personally think that probability is far from negligible at the moment, given the information we have, but that's the kind of discussion you can have with the Bayesian point of view. You can talk about the probability of arbitrary proposition. For example, you can talk about the probability that an unproved theorem is true. Mathematical theorem is true. Now, how can you possibly do that? Because we know either mathematical theorems are, well, certain class of mathematical theorems are either true or false. But if nobody's proved the mathematical theorem, we don't know, right? We can guess. You can make an educated guess about the probability that a mathematical theorem is true. But that's a good example. Even though we may believe perfectly well that it's either true or false, we might still talk rationally about the probability of a theorem being true. But more to the point in social science is to think about hypotheses or theories. So a hypothesis is some kind of picture or assumption about the way a system works, like the economy as a whole, or in Kyle's case, what's the behavior of some individuals under certain circumstances. We'll talk about that quite a bit, as a matter of fact. And the Bayesian setup is designed in particular to talk about the probability of hypotheses. And in particular to talk about the probability of hypotheses conditional on some information or data. So the whole setup of Bayesian reasoning in probability, which if you're interested, you can look at this wonderful book of E.T. James's called Probability Theory, the Logic of Science, where he develops this point of view in what I view as a brilliant and very convincing way. So the sense of probability, this Bayesian sense of probability, is very closely connected to information. In fact, we'll see that once we understand information theory a little bit that it's very closely connected in a formal sense. Since one's degree of belief in anything depends on the specific information you have about it. So the notion we have here is a kind of an iterative notion that we start with some idea or some hypothesis about the world, and we go and look at data or information about it, and on the basis of the information, it either strengthens or weakens our belief in that particular hypothesis, or suggests another hypothesis altogether. I'll give you an example of that in a little while. So the laws of probability, just to get the notation straight, about propositions or hypotheses or whatever the objects that we are going to talk about, is works like this. A proposition is any kind of statement that might be true or false. Propositions could include measurements of quantitative variables. What's the temperature going to be in Central Park tomorrow at noon? Hypotheses, statements of fact about the world, which we might not know about. Did Mycenaean civilization collapse because of an invasion of Doric peoples from the north that overwhelmed it? Or did it collapse because of contradictions in its internal economic institutions that led to some kind of riots, or some kind of revolt or rebellion that destroyed the palace civilizations? Now, one of those two things is probably true. Maybe they're both sort of true or something like that. But we don't know, because you can't tell from archaeological evidence what started the fire. You can find the roof beams in the temple, the charred roof beams that fell down when there was the fire, but you don't know whether the fire was started by the Doric invaders or it was started by a rebellious mob in the palace that was taking over the palace. Okay. The marginal probability of a statement is just the probability of the statement by itself. So that's called the marginal probability, and you want to keep that in mind. And it's a measure of the degree of belief that P of A is the measure of the degree of belief that A is true, and it varies from 0 to 1, just like all probabilities. Can't be negative, can't be bigger than 1. The conditional probability of B, of one proposition B given a proposition A, is written PB with this vertical slash A, and that's the degree of belief that B is true given that you know A, that you know that A is true. The joint probability of A and B is called the probability of AB, is the degree of belief that both A and B are true. Okay, it's very important in working with these probabilities to understand what's called the product rule. The product rule is the most important rule. And many people have the product rule wrong. For example, many people get taught sometime in high school or something that the probability of that the A and B are both true is the product of the probability that A is true times the probability that B is true, the product of the marginal probabilities. It's very important to realize that that is not true. That's only true in a very specific and special set of circumstances. The general logical rule is this, that the joint probability that A and B are both true is equal to the probability of B conditional on A being true times the probability that A is true. Or you can see by just switching A and B that that's also the probability that A is true conditional on B times the probability of B. So you have two different ways of writing joint probability from this way of thinking of things. And you'll notice that neither of these says that it's the product of P of A times P of B, of the marginals. The only case where it's going to be the probability, the product of the marginals, is in the case where the probability, for example, that B is true conditional on A doesn't depend on A and is just equal to the marginal probability of B. So and that's often called independence. That says that B and A are independent, probabilistically independent of each other. But you're much safer, especially in social science, because we know in economics and social science that nothing is independent of anything else. That's the whole problem of social science and economics. Everything depends on everything else, one way or another, indirectly or by some chain of causation. So you really want to keep in mind the conditional probability. Now, an alternative would be to define conditional probability in this way. The probability of B conditional on A is the joint probability that A and B are both true divided by the marginal probability that A is true. You see, that's just the same as this expression up here. And that is only going to make sense if the marginal probability of A is not 0. If the marginal probability of A is 0, you cannot use this principle because you will get completely off. And you can say to yourself, oh, I'm not the kind of person who's going to divide by 0, so I'm never going to make that mistake. But you're wrong, because everybody makes that mistake all the time and can get very, very confused by it. Okay, then the last part of this slide emphasizes this fallacy that the product rule is that the joint probability of A and B is equal to the product. There is a clear connection or clear implication of the logic of probability that if you believe A is false, you have to believe that not A, which we generally write A with a bar on top of it, is true. Now, let me just backpedal a little bit from that. There is an issue of what's called the law of the excluded middle, and there's also, which Hegel talks about in terms of the negation of the negation. So what this rule, the complement rule, says is that the negation of the negation is the proposition itself, right? That if not A is not true, then A must be true. That is not really correct for the way that we operate in real life. And the reason for it is that we don't actually keep track of all the possibilities. This is the fallacy. It turns up in Sherlock Holmes, and I sometimes call it Sherlock Holmes reasoning. At one point in the Sherlock Holmes story, Conan Doyle has Sherlock Holmes say, here's how it works, Watson. You must eliminate all the impossible contingencies, and whatever remains, no matter how improbable, must be the truth, which is exactly this law of the negation. But we know that that's not true. in real life. You know that we can never keep track of all the ways that a particular proposition may be false, even if this is the way that we reason in probability theory. One interesting point is that all of the implications of probability theory can be derived from the product rule and the complement rule. In fact, you can derive them all from an even simpler rule, but it's a little more complicated to state, so I'm not going to go into that, but you can look into that. So, a system of Bayesian probabilities assigns non-negative numbers summing to 1 to the universe of propositions or hypotheses that are under consideration. In many important cases, the propositions or theories assert something about the frequency with which we're going to observe particular outcomes. Okay. This distinction is also very hard for some people to keep in mind. The distinction between a probability and a frequency. Frequency is how often you see a particular thing in observation or in the real world. The probability is the degree of belief that we assign to the hypothesis or a proposition, which in many cases is a proposition about frequencies. So if you really think about this right, you have to have this two-level conception of what's going on. The hypotheses are often frequencies, and the themselves. Well, let me give an example, and then I'll tell you another story. I think it's the right time to tell that story. Okay, so here's a very common statistical problem. We're supposed to infer the composition of an urn. Okay, so an urn is a big jar, and it's got some balls in it of different colors. And we can't see in it, but we can reach in it and pull out balls of different colors. And we do that. That's called sampling. And the idea is to figure out what the composition of the urn is, or given that we pull out 10 balls of different colors. Let's suppose, which is actually a pretty strong supposition in real life, that we know that there's only 3 colors, possible colors of balls in the urn: red, green, and blue. Okay. Now you see why that's very closely connected to this law of the excluded middle, because how do you know that? Maybe there's a white ball somewhere down in the very bottom of the urn, or a black ball, or a chartreuse ball, or one of these spinning beach balls from the Apple computer. Who knows what's in there, you know? We don't know. But anyway, let's suppose for the moment we do. So this R and G and B represent the number of balls of each color. The size of the urn is the sum. The frequencies of the color in the urn are the ratios. So R over N is the frequency of red, G over N is the frequency of green, and B over N is the frequency of blue. What degree of belief P of A do we put in the statement A, the urn has particular frequencies R, G, and B? This is a very typical problem, and you can reformulate a lot of econometric problems in this. For example, we'll talk quite a bit about quantal response. In this case, the urn is a human subject. And a sample means presenting the human subject with some kind of experimental choice or condition. And we observe whether the human subject did one thing or another. Those are the colors of the balls in the urn. So that would be an example of this. But you can see that the probability of A is a degree of belief in a particular frequency of the balls in the urn. It is not the frequency of the balls in the urn. It's a belief in a particular hypothesis about the frequencies. And the basic way that you solve problems of this kind, in my view, which I would strongly urge you to take very seriously and to try to think about, because you can learn a lot about science and life, in fact, in thinking this way. Bayes' theorem is an interpretation of the definition of conditional probability. Suppose we have some hypothesis or theory, H, all right? The theory in this case is there's 30% red, 20% green, and 50% blue. Okay, that's a hypothesis. Theory H, and we want to determine whether some particular empirical data or observations, D, support or contradict the hypothesis. So what is the data in this case? Okay, we pulled 10 balls out of the urn. 2 of them were red, 1 of them was green, and 7 were blue, or whatever it might be. That's the data. So what does conditional probability tell us? It tells us that it makes sense to talk about the probability of the hypothesis given the data, and it tells us exactly what that is. Here it is. It's the probability of the hypothesis, the degree of belief we would have in the hypothesis if we didn't have any data, the marginal probability or prior probability of the hypothesis, multiplied by the conditional probability of the data given the hypothesis. Now, in order to make that a well-defined probability, you have to divide it by the probability, the marginal probability of the data. That is, over all the hypotheses, what's your marginal probability of the data? But in fact, this turns out to be just a normalizing constant. All of the action in almost all circumstances is just in this product of the prior probability and what's called the likelihood function in that sense. In Bayesian jargon, P of H given D is called the posterior probability of the hypothesis given the data. P of H, the marginal, is called the marginal or the prior probability of the hypothesis, what we would believe if we didn't have any data. And P of D of H is given H is the likelihood, the conditional probability of the data given the hypothesis. It's very important as you're thinking this way to realize that the likelihood, when we consider it as a function of D, is a normalized probability. Because the hypothesis should define, in a well-defined way, the probability that you would see the particular data given the hypothesis. So in the case of the urn problem, what that means is if it was really true that, let's say, 1/3 of the balls of the urn were red, 1/3 were green, and 1/3 were blue, as the hypothesis, what is the probability if you pull out 12 balls, you'll get 6 greens, 4 blues, and 2 reds? And you can see that that is related because it depends on how the balls got mixed up in the urn, even if they were 1/3 one way, or which ones were on top, or something of that, something of that kind. The likelihood considered as a function of D is a normalized probability, but the likelihood considered as a function of H is not normalized. Okay? The only way you make it normalized is by dividing through by this P of D. But look at what this is telling you. This is telling you, I have a bunch of ideas. Suppose my hypothesis is that all the balls in the urn are red. Okay? That's the hypothesis. Suppose initially I say, well, I don't know what the likelihood of that is, but I don't know who packed that urn, and maybe that's the kind of person they were, and that's just, I give that a certain prior probability. I reach into the urn and I pull out a blue ball. What happens to the probability that all the balls in the urn were red? It goes to 0 instantly. Why? Because on the hypothesis that all the balls in the urn are red, what is the probability that I'm going to pull out a blue ball? 0. Okay? Now this way of thinking, I mean, you can play around with this and do interesting probability exercises and stuff like that. But I urge you very strongly to think about this from an econometrics point of view. Okay? What we're really concerned about is hypotheses, and we're really interested in what the hypotheses have to say about the probability that we're going to observe the data that we do. And what Bayes' theorem, this is often called Bayes' theorem, is telling us is that those hypotheses that make what we see more likely are themselves more likely to be true. Now, that doesn't mean that automatically makes them super true, because maybe the prior probability of that hypothesis is very low. But whatever the prior probability of the hypothesis was, if it tends to predict what we see, that makes our degree of belief in it stronger, which is the basic idea here. So you can think of Bayes' theorem as a kind of updating algorithm. We start with some state of knowledge that leads us to some prior assignment of probabilities among all the hypotheses. We look at the data. We ask ourselves, given any one of these hypotheses, how likely would it be that we would see this data? And that updates. Now, does that mean that we eliminate or reject any hypotheses? No, only in the case like pulling the blue ball out of the urn does reduce the probability of the hypothesis that all the balls were red to 0, right? What does it do to the probability of the hypothesis that all the balls were red except 1? Well, it still makes it pretty unlikely, because if all the balls were red except 1, the probability that I would pull out the one non-red ball is pretty small, right? So still not a very likely hypothesis. Let me give you another example, because I think it's amusing, and if you're teaching this stuff, it's the kind of thing that sometimes makes people sit up and take notice about prior probabilities. Patient, maybe it's you, is being tested for a rare condition that appears in 0.01% of the population. This test has 1% false negatives and 2% false positives. So a false negative is you take the test and it says you don't have the disease, but you really do. False positive is you take the test and it says you have the disease, but you really don't. Okay? Okay, the test comes back positive. What's the probability of the hypothesis that you actually have this condition? Now, this is a pretty good test, right? 1% false negatives and 2% false positives is pretty good for medical testing, or almost any kind of testing. So you might think, but gee, this patient probably has the condition. They tested positive. But look at what Bayes' theorem tells you about this. In this case, the prior probability that the patient had the disease is 0.0001, right? 1/100th of 1%. The data is the positive outcome of the test. The likelihood of a positive outcome of the test, given that the patient has the condition, is 0.99, right? Because there's only 1% false negatives. From Bayes' theorem, we have that the probability that the patient has the disease, given the positive outcome, is going to be the prior probability times the likelihood, which is 0.0001 times 0.99 is 0.00099. That is somewhat less than 1/10 of 1%. Why is this? Because the probability the patient didn't have the disease with this data is the probability of the patient not having the disease times the likelihood, which is 0.9999 times 0.02 is about 2%. So of the positives on the test, the huge majority are people who don't have the disease, because the disease is very rare. So it is true that the positive outcome, and then if you normalize these probabilities by, you'll see that what happens is that the probability that the patient has the disease goes up to about a little less than 5%. And the probability that they don't have it goes down to a little bit more than 95%. So the test definitely changes your diagnostic condition, but it doesn't change it nearly as much as you might think, or as many people think, if they're told that the test is good enough to have 1% false negatives. Which makes some people say, well, if I tested positive, then it's 99% likely that I have it, right? But that's not really the right way to think about this. Okay, try one more. Coin tossing. Everybody likes the idea of coin tossing as an example. So this is the Bernoulli trials, where you have either a hit or a miss. Hit might be a head, miss might be a tail. Incidentally, there's a man named Percy Diaconis, who is a professor of mathematics and statistics at Harvard, who has trained himself to toss coins with 99% probability that they'll come up either heads or tails. So if you are watching somebody toss a coin, you want to know who that person is exactly, and just if you're going to bet on heads or tails with that person. Okay, so we think if we're frequentist probabilist, you think, well, let's run this experiment a whole lot of times, toss the coin a whole lot of times. We would think that the number of hits, the fraction of hits, is going to approach some limit. This is often called the law of large numbers, right? P. And the value of P is the hypothesis. What's the data? The data is that we only saw a finite number of coin tosses, and we saw n1 hits and we saw n2 misses. Given P, the likelihood of observing n1 hits in n trials is the binomial probability, right? It's the combinations of n things taken n1 at a time times P to the n1 times 1 minus P to the n minus n1 power. Okay, and this is just the definition of the choose n1. It's all the possible ways of arranging the n things divided by permuting the first n1 and the other ones. So we might adopt a uniform prior. So we're going to say, okay, my probability that P is in the range P prime plus some dP is dP if P prime is between 0 and 1, and it's 0 otherwise. So I'm sure that it's the frequency is between 0 and 1, but I don't know. Between 0 and 1, it's just uniform. I'm just going to treat it as uniform. So from Bayes' theorem, we have the probability that P given n1, n2 is proportional to this prior times the probability that we would see n1 or and n2 hits and misses, given that the underlying frequency of hits was P. Well, we just calculated what that was up here from the ordinary binomial probability law. So what that's going to be is it's n over n1 times P to the n1 times 1 minus P to the n minus n1 dP for P between 0 and 1, and it's 0 for anything else. because we know that you can't have negative number of hits or more than 100% hits. In particular, from this, you can calculate the posterior probability of observing a hit in the next trial, which is actually proportional to n1 plus 1 over n plus 2. This formula is a rather famous formula because Laplace used it, and it's called Laplace's law of succession. And here's how Laplace thought about it, or this was the example he gave. He says, what do you think is the probability that the sun's going to come up tomorrow morning? And how does that depend? Well, he said, well, that's going to depend on how old you are. Because suppose you're 1 year old. You saw the sun come up 365 times, right? So that means that you saw n1 was 365, all the times the sun came up, out of n, which was 365. Does that mean you're certain that the sun's going to come up tomorrow? No. In fact, your posterior probability is 366 over 367. If you started off, and if you're a person like Laplace, you would start off this way with the very agnostic view that the probability the sun is going to come up tomorrow could be anywhere between 0 and 1. Right? But as you see it come up more and more often, your posterior probability is constantly being pushed towards a high level of it. Does it ever get to 1? Are you ever sure that the sun is going to come up tomorrow? No. You're a 90-year-old person. Well, you can work out what 90 times 365 is and so forth. You get a very high posterior probability that the sun's going to come up, but how do you know? So here you can visualize this. Here's the probability of a hit. So this is the posterior probability of P, which goes along here from 0 to 1. And we have here a sample size of 65. It's a little hard to see, but N1 is 28. Well, suppose though N1 was higher. What happens? Well, your posterior probability moves over to represent the amount of hits that you saw. Or if you go the other way, it moves down, right? What happens if your sample size goes down? Well, if you keep the number of hits the same, it is going to move over. But if you keep the proportion of hits the same, what happens is it gets wider. I mean, that's just the sampling variance point. Now, one important idea here is that if you're a Bayesian, this posterior probability puts some weight on all of the P's, right? So what you're really doing as a Bayesian is you're being a very cautious person. You're not saying, okay, I saw 10. All right, let's make this 10 out of. Let me move this down to 10. I saw 10 out of 50 hits. Now, if you were a frequentist, you might be tempted to say, well, the probability is probably 20%, right? Because that's what I saw. The Bayesian is much more cautious. The Bayesian says, well, it's most likely that the probability, that the frequency is 20%. But I don't necessarily believe the frequency is going to be 20%. I'm going to give some posterior probability to every P. And when I bet on this, I'm going to allow for all the possibilities. So I'm not going to reject any hypothesis and set it to 0, except P equals 0, because you know that there was at least one hit, and p equals 1 because you know there was at least one miss. Okay, let me give you one more. I think I'm going to skip. We will usually take a break in the middle, but because we got started late today, I'm going to not do a break. But let me tell you one story, because it's a very amusing story that makes these points that Jaynes discovered. This story is told in a lecture of Jaynes's called the Brandeis Lectures, which you can find in his collected papers on statistics and statistical physics, a 1978 volume, which I think I cited in the syllabus. And it's also in some other of Jaynes's writings. But the story is really quite interesting. There was a man named Wolf in the 19th century who decided he would test the laws of probability as an empirical proposition. Because, and Jaynes loves this, because this is exactly what Jaynes calls the mind projection fallacy. That people take probability, which is really an account of the degree of belief of somebody observing the world, and they project it into the world itself as an uncertainty. So Wolf was clearly doing that, so he wanted to test the laws of probability. So what did he wind up doing? He made a machine to throw dice. And this was, in the 19th century. Now we would, run a computer or something like that. But he actually had this machine throw dice, and he had somebody, probably a graduate student, stand there and count how many times each number of pips came up on the dice on each of these throws. And he did a lot of these trials, about 20,000. Now the dice, Jaynes tried to find the dice, but he never was able to find the dice. Maybe some of you can find the dice if you go to Europe, but it would be very interesting to find these dice for a reason which you will appreciate in a moment. Jaynes, however, the data, the raw data of that the graduate student wrote down does still exist. The tabulation of all of these trials. Now, if the laws of probability, if you're somebody like Wolf, are true, what's the average number of pips you're supposed to see? So you throw the two dice, comes up a 7, 5 and 2, or 3 and 4, or it comes up a 2, 1 and 1, or it comes up 12, 6 and 6. What's the average number supposed to be? Closer. There's two dice, 3.5, right? Per die. 7 for 2 die, or 3.5 for 1 die. Well, it turns out that Wolf got about 3.6 or something like that. Does that sound, in 20,000 trials, what do you think? 20,000 trials is a lot of trials, right? What's the square root of 20,000? About. Some 100, something like that. So, does this sound right? Well, it didn't sound right to Jaynes. And he did the following thing. He said, well, if you maximize entropy, which we'll learn about in a moment, subject to the constraint that the number of trials is given, you're going to put a very high peak on 3.5. And in fact, with the entropy formula, the chance that you would get 3.6 is tiny. I mean, it's astronomically much lower than 3.5. So Jane said, well, why is that? Well, he says, well, first of all, how did they make these dice? They were wooden dice. They cut a piece of wood into what they thought was a cube. And then they dug out the dots. So the sixes, they dug out 6 little pieces, and the one, on the other side, they dug out 1. And on 3 and 4, they did the same thing. Now, if you do that, what happens to the weight of the die?
Lopsided.
Which side is heavier?
The lower side is heavier.
Yeah, the 1 is heavier. So what are you more likely to see, 1 or 6? And you're more likely to see, because the one side will tend to fall downwards. Okay, so right there, you get a bias in favor of more seeing a higher number of the dice, a higher number of pips on this experiment. Now it turns out that when you allow for reasonable size of the gouging out the pips, that the mean went up to something like 3.55. I can't remember the exact numbers, 3.55. And that's going in the right direction because he got 3.6, right, in the actual data. But Jane says, well, but that's still very unlikely from an entropy point of view. That deviation between even 3.55 and 3.6 is an enormous probabilistic difference. So then Jane says, well, when they cut this cube, they must have cut one dimension of it shorter than the other. And he puts that in the formula, and it goes up to 3.58 or something. And then he says, but you know, 3.58 is still, or down to 3, whatever, the entropy is still way off. So now what? Well, he said probably there was a chip on one of the corners of the die, which explains the remaining discrepancy. Now, what's important about this is not necessarily the exact formulas, but the process that Jane's is going through, because this is absolutely fundamental to the way I'd like to get you to think about economic hypotheses. So what Jane starts with is he starts with a very general hypothesis. He's going to maximize entropy subject to effectively no constraints, right? And he sees that that hypothesis doesn't give a very high posterior probability. So what is his reaction? Does he reject the hypothesis? No, he says, that's just when science clicks into action. That's when the fact that the simple hypothesis did not explain what was going on, that we need to find a plausible further constraint, such as the digging out of the pips on the die. And you go through this cycle again and again until you have nothing left to explain, because the maximum entropy, which is maximum uncertainty, has been reached. Jose.
How do you know that your initial hypothesis is pointing you in the right direction?
Well, that's a good question. And of course, in this case, the thing is cooked a little bit. That's where you have to count on being a heterodox economist who has a good understanding of the real economic system rather than a neoclassical economist who's starting from the wrong starting point. Although you'll see that, that an implication of this would be that the neoclassical economist and the heterodox economist faced with the same data are supposed to converge, right? Through this hypothesis, which is an interesting question as to why that so often doesn't happen. But think about another aspect of this wolf thing. So that paradigm, you pick a hypothesis, you look at observation. If you're especially interested in the case where you have some reason to believe the hypothesis, but it doesn't explain the data. That's when things get interesting. Okay. But think about a third aspect of the Jane's story. Here's Jane's 150 years or something after these dice were thrown. And he is able, from just analyzing these records, to make very plausible inferences about the shape and the perfection and the depth of the gouges and all that stuff in the die. So this is a very important aspect of the Bayesian pattern and Bayesian reasoning. It allows you to find out from what you do know stuff that you don't know. Well, it doesn't allow you to find it out with probability 1, no. But it can hugely change your information state and give you very strong reasons to believe something particular that you don't know because of something that you do know. Well, that is very interesting for economists, because we're always stuck with that, right? The amount of things we don't know, what's the ratio of the amount of stuff we don't know to the amount of stuff we do know in your personal experience as an economist? Well, in my personal experience, that ratio is enormous. I mean, the stuff we don't know is hugely much greater than the stuff we do. We have some information about. So this way of thinking about information and inference is, in my view, the most promising way to think about it, rather than frequentist methods, which basically consist of sort of guessing. Okay, so the final preliminary topic here is, which is very closely connected to probability and frequency, is information theory. And information theory actually has a long history, and we'll talk a little more about it next week. But it kind of came to a head in 1948 when a man named Claude Shannon, who was working at the Bell Labs, wrote a paper in which appeared what's often called Shannon's theorem. And effectively what Shannon's theorem was a definition, a quantitative definition of the measurement of information. And that has been hugely influential. Like if in every field except economics, curiously enough. But I mean, transformed communications, information theory, statistical physics, biology, and everything. But so far, except until this room, not economics. Maybe I'll persuade you to go down this road. So what was Shannon was looking for a quantitative measure of information. And that's not such an obvious thing. The reason he was interested in it was because he worked for the Bell Telephone Company. So he was interested in finding a tool to discuss things like the maximum capacity of an information transmission system, which we now typically call bandwidth. It's a very, very typical way of thinking of it. Telegraph wire, telephone circuit, or a fiber optic cable. And here's how Shannon set up the abstract math of this. He says, well, let's suppose that there's a finite set of n messages that some transmitter is trying to send to some receiver. Was that? No, you're just, okay. And they both know these messages. Okay, my favorite example is Paul Revere, right? 1 if by land, 2 if by sea. What if they didn't, what if the British weren't going to march at all that night, or go up to Concord anyway? Well, anyway, so we have one light in the North Church was going to be by land, and 2 if by sea, but which meant by water, by going up the Charles River. Okay, so you have a finite set. In that case, there's 2 messages, but it could be more. It could be the letters of the alphabet. It could be a huge number of messages, because it's ends. It's finite, though. One scheme to transmit the messages is just to agree on a numbering of them. So we call message 1, 1, we call message 2, 2, 3, 4, 5, and so forth. And then we're just going to transmit the number of the message, whatever it happens to be. For example, this message might be, which horse won the race? Where is the submarine right now? Or a number, I mean, information is very, is very pervasive. It's all over. Well, if you did that, you would require log to the base 2 of n bits of information, right? Because you're going to have to send a number between 1 and n. And the binary coding of numbers between 1 and n requires log to the base 2 of n bits. So that's what you're going to have to send. The time it's going to take to send that message depends on how many bits of information your channel can transmit in a given time. Now, if you're Paul Revere, it took Paul Revere a good 6 or 7 hours to get out to Concord, right, on his horse. So he was carrying 1 bit of information, a very important bit of information, but just 1 bit, right? So that communication channel was not a hugely high bandwidth communication channel, even though the message was very important. Now, Shannon notes, which is very commonsensical, that if some messages are sent more often than others, although it's one of these commonsensical, obvious things that geniuses, that make people into geniuses. Okay. He says, okay, so suppose you're going to send some of the messages more often than others. Let's say 9 out of 10 times the British go by water, and only 1 out of 10 they go by land, or something of that kind. You can improve the average transmission rate of the communication channel by assigning short code words to the messages that are more frequently transmitted. Now, you see this, for example, in Morse code, right? Letters like E and T are dot and daw, which are the shortest codes available in the Morse code. And letters like W is di-daw, daw, daw, or Q is daw, daw, di-daw, and so forth. So you take the ones that take a longer time and you assign them to messages, or in that case, letters that are less frequently transmitted. So suppose there's a frequency, f sub I, which is non-negative. Now, if there's, what if fi were 0? You wouldn't bother to give a code word to that message because you would never send it. Yes, that's right. Okay, so you're only dealing with messages you're going to send sometime, maybe not very often, but some of the time. And the frequencies add up to 1. They're non-negative, and they're positive. They're strictly positive and add up to 1. What Shannon proved was that you can devise a coding in which the ith message is assigned a code word of this formula, log 2 to the frequency of the frequency. Then this symbol, these little square brackets, are called the ceiling. So because you can't, you have, bits come 1, 2, 3, 4, 5. I mean, you have to have a integer number of bits. So you take log 2 minus log 2 to the fi, you might get a fraction. So you have to go up to the next higher integer in order to make the formula exactly right. And furthermore, Shannon showed that this is the very best one can do to minimize the average message length as the set of messages becomes large. That is, as the n goes to infinity. Several of these ideas are going to come up over and over again in the course. So I just want to give you a little preview. A set of messages with specified frequencies is often called an ensemble. So an ensemble is a set, a finite set, together with associated frequencies that add up to 1 and are all positive. Secondly, if we take the logarithms to base e, the measure of information is called the net because of natural logarithm. When we take the logarithm to base 2, the information measure is a bit. I'm going to generally use bits because we are much more familiar with bits because we mess around with computers and pixels and all that all the time. And then the ceiling notation. So then Shannon's theorem says the following thing. He says, well, what is the average message length for an ensemble? Well, the average message length is going to be what? Well, for the ith message, the length of it is the log minus the log of fi. Now remember that these f's are fractions, right? Because they're frequencies, so they're less than 1. So the logarithm of a fraction is what kind of number? It's negative, right? So you have to put this minus sign in front. So if I have a fi that's very small, I only send this 1 out of every million times. What happens to the code word that I assign to it? Becomes very large. So you have this inverse relationship between the probability and the length of the code word. The smaller is the probability, the bigger the code word. Suppose I was sending a message. I have one message I send half the time. Should make that a very short code word. Now, if you start thinking that way, you start to see some other subtleties of this. Can I make that code word just 1 bit? Yes. Okay. So if I send 1, that's the message. That's the message I send half the time. What kind of code words do I have to give to all the other messages? What do they have to start with? Which is, what's the only other thing if we're using bits? It has to start with a 0. So the next most frequent, shortest message I can send is what? 0, 1. Well, if I'm lucky enough to have another message that I send 1/4 of the time, that is 1/2 of what's left, then I would assign that to that. Then what do all the other messages have to start with? 0, 0. And I can keep going in that, so you can start to see that you have to have what's called a prefix-free code. Why can't I use the message 1, 1? Why can't I use the code word 1, 1?
Because you don't know if it's 1, 1 or 2, 1.
Exactly, because the 1, when you as the receiver get the 1, you think, oh, he's sending the 50% message. So I can't use the 1, 1 to distinguish. I have to. The only way I can distinguish is to send a 0, and then some more. some more data. Okay, so the average code word length is going to be the length of the code word for FI times the frequency with which that code word gets sent, which is just FI. This is a very important formula. It may be the most important formula of your whole life, but you just don't know it yet. It's quite a remarkable, I mean, it is hard to see why. I mean, it looks like just an ordinary formula, right? But it's actually very, its implications are extremely far-reaching, as we'll see. Well, what's the worst case? The worst case is that all the messages are sent with equal frequency, which namely 1 over n, since they're n messages. In that case, the informational entropy is going to be the sum of 1 over n times the log of 1 over n. Well, the log of 1 log of 1 over n is what? Minus the log of n. Minus the log of n is the log of n. Add up n of those, and you get log n. So log n is the maximum entropy of an ensemble of size n. And you'll notice that that's exactly the pickle we were in when we were sending the messages just by their number, right? That's how big the code word had to be. We had to send the whole number, which would have been n bits every single time. There's no way you can shorten that up. Suppose one of the n messages would be sent every time. So f1 is equal to 1, and all the rest are equal to 0. What's the informational entropy? Well, the convention is that you set 0 times log of 0, which is actually indeterminate, because log of 0 is minus infinity. You set it equal to 0, because it never happens. And what it really stands for is a very long code word, but it never happens. So the entropy is 1 times the log of 1, which is 0. So, but in the case where only one message gets sent, what's your informational state? You don't need this message, right? You already know what happened. So it's in this sense that intuitively that Shannon's measure is a measure of the uncertainty of the receiver in this kind of a model. Or you can put it another way, it's a measure of the surprise, the average surprise that the receiver has when she actually receives the message. And in that sense, it's a very intuitive, quantitative representation of information, of your information state, of the amount of information that you get by receiving this message. Let me then make one final observation, which is that there's a kind of converse to Shannon's theorem. So what Shannon's theorem says is to every frequency distribution over a finite set, there corresponds a code length assignment. Notice that Shannon doesn't tell you what the code has to be. We started to work out the code with this 1, 0, 1, and all that stuff, right? That's the actual code. But what he's talking about is just the code length. So the code, the message that's sent 1/4 of the time has to take up 2 bits, right? Okay. But think about this the other way. Suppose that I come across a system that has a whole bunch of code words of different lengths. that tells me if the designer of the system was trying to do it optimally, it tells me what the frequencies are. Because just as the code word length is minus the log of the frequency has to be e to the minus code word length. Now this actually has quite a few implications for economic data. We will use this fact. Okay, now that actually, remarkably enough, with 3 minutes left before the end, gets me to the end of my prepared talk. But we have 3 minutes, and if anybody has a question, if you are still, if your neurons are still functioning.
Could you elaborate on how this channel's entropy is related to Bayesian reasoning? Because you used just a little Bayesian idea and then you just ended with the Shannon's entropy, right? So what is the relation between these two different topics?
Oh, the Bayesian and the information level. Well, for example, you can, one simple thing is, suppose that you're the recipient of the message, and you haven't received the message yet. What probability do you give to each state of the world? Well, each message that you might receive. Pretty much you have to give 1 over n, right? You receive the message. What probability do you give to the state of the world? Well, now you've received the message, so you know what the message is. Let's say it's a noiseless transmission channel. You know the state of the world, so you have no uncertainty left. So your entropy has gone from maximum, log n, to 0 by receiving the message. Well, let's make a more reasonable story, because it's a very interesting question. How about if this information channel is noisy? And what that means is that whoever's sending the message, the code word, puts the code word into the information channel, but what comes out of the information channel sometimes isn't the code word that was put in. Maybe one of the bits gets scrambled or lost under the Atlantic Ocean or something like that. Now, what happens to your state of Bayesian posterior probability? It is not reduced to 0, but is it reduced? Yes, because the likelihood, now your hypothesis is, which message did he send, right? Given the hypothesis, there's a certain probability that you would receive any particular message. Now, if that probability is uniform, that is, whatever the guy puts into the transmitter, you get back just, a uniform distribution, then this information channel is no good whatsoever. It can't transmit any information. But let's say it's not that bad. It just flips bits every once in a while. Then you can write down through the Bayes theorem what your posterior probability is when you receive a particular code word as to what was sent. And it won't reduce your uncertainty to 0 because you have the noisiness of the channel to contend with, which, as we know in economics, we have very noisy, bad data, typically. Okay, it is that. So next week, we will start in on the information constrained or entropy constrained behavior idea, which answers the question of where does maximization come in and what's its interaction with this information idea.